Okay, this is Physics 1102. This is chapter 27, and this is on early quantum theory and models of atom. All right, so we're skipping chapter 26 of relativity. It's an interesting topic, but it's beyond what I think is scope of this class. So this will be the first chapter for exam 5, and this is also related to labs 11 and 12. 12 is on the hydrogen 11 is on the hydrogen spectrum and spectrum of gases, and 12 is on what we call blackbody radiation. So these two labs are directly related to this chapter. So, what do we do here? All right, so we're gonna go on here, and you know, we talked earlier about, in the earlier chapters, electricity, and you know, we have a moving current in a wire of charges of some sort. All right, so the idea of electricity goes back a very long time. However, what was exactly the what is doing this thing? We know now they're called electrons, is what provides that. But electricity originally was thought of as sort of a fluid that flowed through the wire, much like water flying through a pipe. It was all thought to be originally a fluid. And then in 1897, J.J. Thomson an English scientist, discovered the electron. I'm not going to get into the details of that, but that was thought, you know, that was the electron, right? So rather than being this fluid, it's much like atoms in water. All right, it's not divisible infinitely, but you have individual atoms and molecules that make up, say, water, gas. It's the same thing. You have individual particles known as the electron that provides the current. Mass together provides the current. And the charge, as we've had, Q, or E, I should say, is minus 1.6 times 10 to the minus 19th coulombs. Okay. And then it was discovered in 1911. Okay. In 1911, Robert Millikan by doing what we call his oil drop experiment, was actually able to figure out the mass of the electron. So the mass of electron E is 9.1 times 10 to the minus 31st kilograms. So extremely tiny object. So that's the date of what we know about the electron. There's the charge, and there's the mass. Now while we're at it, then, all right, so while we're at that, the proton, P, has a positive charge, 1.6 times 10 to the minus 19th coulombs, and its mass is 1.67 approximately times 10 to the minus 27 kilograms. So the mass of the proton is approximately 1,800 times the mass of the electron. So even though they have the exact same charge, opposite charge, it's 1,800. So in a real nucleus, a real atom, almost all the weight is in the nucleus of the atom, which we'll get into later. All right? So that's the first introductory part on 27.1. Okay. Moving on then. We have, when you see, look at the lab 12, it'll talk about blackbody radiation. And an example is either a light, the sun, which is a temperature of about 6,000 degrees Kelvin, or an incandescent bulb, which has a temperature of about 3,000 degrees Kelvin. They're very hot. This is very hot. The bulb invented in 1879 by Thomas Edison was based on heating up a tungsten element, very hot, that radiates radiation. Now, what does that mean? What is the sun? Well, you can look at the lab, but we can actually look at this here. I've got a picture here from the text. And what we have here in green is what we call blackbody radiation of the sun, and in red is the blackbody radiation of the incandescent bulb. So if you sort of plot this, right? And I'll do it red for the bulb. Now, for the sun, light, for the sun, this is the visible spectrum. Okay, you got violet here, red here. So we're actually plotting its intensity versus wavelength. Right. Of light. And this is the visible spectrum right here. Most of the sun's radiation is in the visible spectrum. Now, I think that's maybe why our eyes have adapted to this, because this is where most of the sun's radiation is. The lamp, on the other hand, the radiation is far out in in the infrared. Right, so this is infrared here. This is UV here. So this is shorter wavelength, higher energy. So the light, approximately 90% of the energy from the light is in non-visible heat radiation. So a tungsten lamp basically only puts out about 10% visible light energy. That's why they're extremely inefficient. They get very hot, and that's why we have LED bulbs today, because they put out all their light in the visible spectrum. So this is an example we call blackbody radiation. And it's entirely due to an object being hot. Everything that has a temperature emits radiation. We emit radiation, but because we're only about 300 degrees Kelvin or so, most of our radiation is in the far infrared. Much like the Earth's radiation, it absorbs sunlight and re-radiates as infrared, which creates a greenhouse effect. So that's what we see there as far as that's concerned. Now, related to this, there's a relationship between temperature and the so-called peak radiation, lambda P. So depending on what it is, this peak radiation is lambda P times the temperature of the object is equal to 2.9 times 10 to the minus third. Okay? And the units are millimeters Kelvin, but this is the radiation. So as the temperature gets hotter, this goes down, right? Because this is an inverse relationship. So the hotter it gets, the more it is in that. And you'll see that when you do lab 12 with blackbody radiation, right? So now, based on this thing, energy, another thing, so that's the part there. Okay. So again, this is part of lab 12, which you'll see. All right. So moving on. We can see that 27.3. All right, we have quantized, we have electrons that are quantized. We've talked about, so we have the electron. Well, it turns out energy is also quantized. Meaning it's made up of particles. And we have what we call then the photon. So light is not same thing, a fluid, but it's made up of individual particles. And we'll see this is part of lab 12 also, or lab 13. Yeah. So what? That's true. Lab 12 will be, we talk about the lab with photoelectric effect. And you'll see this when you do the lab, and this is all a simulation, it was discovered by a scientist, Max Planck, a German scientist, discovered that the energy of a photon, E, is given by its expression H times F, where H is what we call Planck's constant and F is the frequency of light. Frequency right? And this is Planck's constant, and it's given by 6.6 here somewhere. I've got it, so I'll make sure you have the right units. .63 times 10 to the minus 34th joules seconds. So this is H, Planck's constant. And that's the value for it. And the way it means is the energy of a photon is given by H times the frequency. So let's do one example. Light has a frequency of approximately 10 to the 14th hertz. All right? So say visible light has that. The energy of an individual photon would be HF, which would be 6.6 times 10 to the minus 34th times 10 to the 14th which is about 6.6 times 10 to the minus 20th joules. It's a very small number. All right. So to compensate for that, all right, to always not be dealing, when we're dealing with energies of small particles, both those of you in chemistry, we have the EV, electron volt, is equal to 1.6 times 10 to the minus 19th joules. It's basically the energy of one electron with 1 volt. So we define this, so then what we can do is this energy, 6.6 times 10 to the minus 20th, times 1 EV per 1.6 times 10 to the minus 19th. So that's about 16 times 10 minus 20th. That's about 0.4 EV. All right? So it's about 0.4 electron volts. That's how we define, generally refer to energy for very small particles. You deal with EV, like ionization energies, you're dealing with electron volts. Even though these are both units of energy, perfectly valid, this one is more relevant for that. Okay. So that's that part there, and this expression, E equals energy is H times that. So this will actually be units of joules or EV, depending on what units you use. All right? So, all right, moving on from there. We have the next thing. That is a so-called photoelectric effect. And you'll see this in the lab. Again, E equals HF. And this was discovered and actually known for a while. And one reason why Einstein eventually got the Nobel Prize, but in 1905, he explained this thing called the photoelectric effect. And what it is you have a metal here, say, oh, I don't know, silver, some metal, right? And if you shined a light on it of some sort, the light would heat this metal up and would emit electrons, right? And what you do then is on the other side, when they heat them up, they would pass over to the other side eventually and create a current, measurable current. So it loop around, you measure current. So you shine energy on this, all right? Hits it, electrons come off, they eventually get on the other side, makes a current come in, and you form a current. Now, what was perplexing was the intensity. To be able to get a current, the intensity had no effect. Right? I mean, you can have an extremely bright red light, but it had no effect on making this thing work. What mattered was the frequency. Frequency, meaning energy of light, given by this expression, is all that mattered. So, what it meant is higher energy, higher energy, meaning higher frequency, was able to get, what happened is photon of one light, one photon of the right frequency would hit one electron, which then sends it out. And that's what caused it. This is what we call the photoelectric effect. And it's why eventually, one reason why Einstein eventually got the Nobel Prize in 1921, because of this discovery. So it's not like how many hit them all at once, but just one of the right frequency, if it's high enough, will actually send it off. And that is known as the photoelectric effect, and it's based on the fact that individual photon has an energy given by the frequency times Planck's constant. And that's what we'll see, and you'll see that when you do the lab as far as that is concerned. All right, so to get into that, you can read the chapter on it, but basically that's what we mean by the photoelectric effect. So when you do the lab, you'll see what I mean, because we'll be looking at different metals here. Some metals, it takes a higher energy to excite electrons out as compared to other metals. So that's what the basis of the lab will be all about. All right. And so what this means is the kinetic energy of the electron. So the kinetic energy of the electron coming out is equal to the frequency of the photon, so HF, minus the so-called work function. And this work function is energy needed to emit the electron from surface. Okay? And this depends on the material. And that's part of the lab. That's part of what you see in the lab. So this is a photoelectric effect, and that is part of section 27.3. All right? So, oh, yeah. All right. All right, so that's that part. So the rest of it kind of gets into details of how that works. But what I'm going to show here is move on to the next section. And this is wave nature of matter. And what that is that electron is a particle and a wave. All right, so much like light is a particle and a wave, electron is a particle and wave. And it turns out the relationship of wavelength is given by h over p, where this is the momentum. This is Planck's constant. This is the wavelength in meters. Momentum of electron. And if you remember from P, way back, first semester, this is mass times velocity. So this is the velocity in meters per second, and this is the mass in kilograms. All right? So, Okay. All right, so what we have here, let's do an example of what we mean for this for the electron. All right, so electron has a mass of 9.1 times 10 to the minus 31st kilograms. A speed of a fast electron, coming out in air might be in the order of 6, let's say 6 times 10 to the 6th meters per second. All right, that's what we have there. So the wavelength of this electron, so the momentum is going to be the product of these two, which would be approximately 5.5 times 10 to the minus 5.55, let's see, that's 55 times 10 minus 25th, 10 to the minus 24th, all right, H, so the wavelength is going to be 6.6 times 10 to the minus 34th over 5 is approximately 1.2 times 10 to the minus 10th meters. So this is about 0.1 nanometers. Now we'll also see this is about the size of a hydrogen atom. This is about the same size as a hydrogen atom. So this is the wavelength of an electron. So what was discovered, since this is about the same size of atom, is about the same size, and since this has a wavelength, it was thought of that maybe we can use electrons as microscopes. Because for light, visible light is around 500 nanometers, and this is about 0.1 nanometers. This is about the smallest. This is the wavelength of light. This is about the smallest that you can use. Smallest object you can see using visible light is about 500 nanometers. So you can't make out any of it. So the electron microscope was developed to take advantage of the wave nature of electrons, and this is how you can actually look at individual atoms and their structure by using an electron microscope. Now, you're not actually literally seeing it, but the device takes advantage of that fact. So this is because light has section, and this is part of section 27.9 talks about the electron microscope. So it's a very, very clever tool. So this principle here, this principal wavelength, it doesn't matter what the object is, all objects have a wavelength to them. And you can figure it out, if you want to figure it out, let's say a ball. Let's take this object. All right, this weighs about a kilogram. And if I was to throw it, so P is mv, and if I was to throw it at 10 meters per second, it would have a momentum of 10 kilograms meters per second. if we plug that into this expression, where again, H is 6.6 times 10 to the minus 34th, and plug that into here, you're going to find a wavelength that is incredibly small. So that's why we don't see wave nature in everyday particles, because it's such incredibly small size. And that's the basis there. So that everything has a wave to it using this expression here. All right? So that's the wave nature of light and how we can take advantage of that for certain things. And all right. And I'm going to leave it at that. I'll talk about the next part tomorrow on the Bohr model of the atom. So this is the first section. This relates to one lab, I think it's